Welcome back everyone. In this lecture I will begin with the definition of functions, and then we will see some important notions related with functions. So, let us start with the definition. So, we want to actually define a function between two sets. So, to begin with, a function is indeed a relation satisfying some property. So, in elementary school, like you must have actually seen functions defined or interpreted in terms of these diagrams. So, what we want some domain on the right side and then codomain on the left side. A function is a map or a association between each element of A to some element of B. So, let us say this capital A and capital B are given two non-empty sets, and we want to define a function. So, which is indeed a relation between elements of A and elements of B with a certain rule. So, what is the rule? Like given element of A and we want to kind of associate some element B here. But if I want it to be a function, then we demand that there exists at most one element that we will associate. So, what is not allowed? For example, if I take some element here, let us say C, then it should not map to two elements like here B1 and B2 here, okay, and this is not allowed. So, this is not allowed, okay, and this is what we are actually going to put it as definition. So, to define, we start with A and B to be two non-empty sets, and then we want to define a function from A to B, which is usually denoted by f colon A arrow pointing towards B, and then you write A to B. Okay. This should be written as read as f is defined from A to B. So, now what is function? Okay. So, f is indeed a relation. So, that means that this is a subset of A cross B. Okay. So, this is actually denoted as this, and the very first property of the function is it is a subset of A cross B. So, that means a function to begin with, it is a relation. So, f is a relation. So, now not it is just a relation, it has to satisfy some property. What is that property? So, let us take some element A in A. Suppose A comma B in F and A comma B dash is in F. Okay. If this thing actually happens, so then we must have B equal to B dash. So, that is the definition. So, we do not want one element mapped to two different elements. Okay. So, we want one element is mapped at most to one element in the image. So, that is what we demand. Okay. So, and for each element of A, you need to actually associate element in B. Okay. So, that is the third property. So, for all A in A, there exists B in B such that A comma B is in F. Okay. So, otherwise in practice what you do, like you do not need to demand this condition 3. So, you just restrict your domain, okay, wherever function is defined, okay, that is actually possible. There is no there is no problem in this condition 3, but anyway, but if you want to call f is a function from A to B, then for each element of A there should be some association in B, okay, that is what we are demanding. So, this is a more technical definition, but in practice you can see that. So, what we are demanding, so given element A in A and I want some element B in B that should be related to A, and only at most one element should be related, not too many elements should be related. So, something like this should not happen, okay. If you are drawing the picture, so if you have domain A and then domain B, and if you have an element A here, and there should not be like too many things going like this, okay, and mapping something here, and this is not allowed, okay, not allowed. So, this is like a very general abstract definition of function, but most often what we would do, like in practice, the functions will be defined using formulas. Like we can use existing trigonometric functions, sine or exponential, logarithm, those kind of functions. Sometimes we can also come up with some like more like abstract way of defining also. Again, functions also kind of adapts so many things, okay. We will see later some examples where we will be able to actually define some functions on some interesting sets that kind of allows us to kind of adapt things from in more real world. Okay, so let us actually look at some examples of a function. So, before that let us actually look at the set of functions that we can define from A to B. So, if you think about it, given set A and given set B, a function is nothing but subset of A cross B. Okay. So, this is what the very first condition actually says. So, f is nothing but subset of A cross B. So, that means, so this actually allows us to think f is an element of a power set of A cross B. So, now if you think about it, then this means if I consider the set of all functions from A to B. So, I can take this set of all functions from A to B, and usually it is denoted by B power A, where A is the domain and B is the codomain. Okay. So, like I said, any given typical function is denoted as f colon A to B. So, this is the like standard notation that is used in order to write function. Now, here this A is called domain and this B is called codomain, okay. And we can also define some other terminologies like image of f or image of any subset of A and so on. We will come to that later, but first try to understand that the set of all functions from A to B. So, this can be thought of a subset of P of A cross B. So, by our axioms, ZF axioms, that tells you that given A given B, I can construct the Cartesian product A cross B, and in particularly I can talk about the power set of A cross B. So, this is indeed a set. Now, if you think about it, this B power A is nothing but those elements f in this power set of A cross B such that f satisfies the conditions 2 and 3. The conditions 2 and 3 are given here. Okay. So, one element should not be mapped to more than one element, and then every element should be mapped to something, Okay. If you just use that definition, then you can see that you are actually collecting some functions some subset elements of this P of A cross B satisfying some property. So, that means this is indeed a set. So, this is indeed a set. Okay. So, like I said, to begin with, F is already a subset of A cross B. So, this is the abstraction that you need to be comfortable with. So, this means functions are indeed sets, and the set of function that are also is indeed set. Okay. So, this is what important. Okay. So, how one actually writes the image of given element. So, like I said, any function is written as f colon a to b. So, now you write, so we write f of a equal to b if a is mapped to b. That means a comma b is inside your f. So, now given T subset of A, so let us say this is given, we can actually define this f of T, or sometimes it is also called image of T. I am talking about f of capital T, and this is defined to be, you collect all possible f of A inside B such that A comes from capital T. So, in particularly f of A is the image of A under F. Okay. So, these are all the standard terminologies that one defines for functions. And more importantly, we also have something called inverse image. So, now what I can do, I can start with S is subset of B. So, then I can look at the pre-image or the inverse image of F, which is denoted by F inverse of S. So, this is indeed what called pre-image of S in capital A, or inverse image of S in capital A, of course under F. Okay. So, this is defined to be, you collect those A in A such that f of A is an element of S. Okay. So, this is what we call it as inverse image. So, like I said, in practice we will use formulas in order to define functions. Sometimes we also need to come up with some other ways to actually define functions, because the way we define the functions very abstractly, that will adopt anything, okay, the defining properties that we need to explain. So, let us see various examples, okay, then it will become clear what we are talking about. For example, I can define a function from, let us say, natural number to natural number such that n goes to 2n. Okay. So, this is a function. So, for me natural number, let us say I am including 0 and 1, 2, 3 etc. So, you are all comfortable with how to add natural number and multiply natural number. In this course, we will actually construct natural number from injective axioms, that I will do maybe in the next class. But I am just assuming that you are comfortable with multiplication and addition of natural numbers. So, now I can also define a function, okay, like f of x from R to R given by, let us say, x goes to x square. and then one can also define a function. So, these labels f, g, h, they are often used to denote the functions. So, sometimes we can also use f1, f2 or f alpha if you want to index the function, and they are generally used. So, you can take g from R to R. For example, you can use some complicated formulas like f g of x equal to like cos x, okay, and assuming that you know how to define cos x. Sometimes you may also kind of define using like more complicated notions. For example, you can define a function from 0 to infinity to r, okay, like x goes to integral 0 to x t square dt. Okay. So, this means what? This means we have actually understood what this integration means. Okay. And similarly, one can also come up with some functions, some kind of weird functions. Okay. And like I said, so we need to kind of tell the rule how to associate given element of the domain to a codomain. Okay. So, this does not need to be algebraically or analytically expressed. Okay. So, that is not important. Sometimes one can actually tell what function actually does. For example, let us take this something like this. So, I want to actually define a function from, let us say, n cross n to n. Okay. So, for example, if I am just interested in just a function, what I can do? I can pick an element here in n, I can send all the elements of n cross n to n. Okay. But there is one very interesting function which is indeed the listing of this n cross n, which tells you that this n cross n is indeed countably infinite. So, I will define the notion of countably infinite and all in the later part of the course. But what it means that we will be able to define an injective function from this n cross n to n. What is an injective function? Injective function is a function which is 1 to 1. So, let us define that a function from a to b is said to be injective or 1 to 1 if whenever you have f of a equal to f of b, f of a equal to f of b, that should imply that a equal to b. That means, if you take, so for example, if you take negation, okay, whenever you take a is different from b, so then that should give, so this will be the negation, okay, this is the negation. Then f of a should be different from f of b. So, if you take two elements which are distinct in the domain, then their images also should be distinct. So, that is what we are expecting. Okay. So, that is what called injective. That means, each element in A map to only unique element there. Okay. So, now if you think about it, this n cross n looks like having more number of elements, okay, because n is given to be 0, 1, 2, etc. So, then n cross n will be tuples of all possible n comma m such that where n and m comes from m. Okay. Usually what happens if you are taking like finite set, so then you can easily see that the Cartesian product of that set with itself will have more number of elements. For example, like take a to be just 1 comma 2, then if I take a cross a, So, the number of elements in A cross A will be exactly the product of the number of elements in A in the finite case. So, which is exactly 4. So, you can denote it by like 1 comma 1, 1 comma 2, 2 comma 1 and 2 comma 2. So, this has 2 number of elements and this has 4 number of elements. So, then one may expect that when you take n cross n, it should have more number of elements than n. But then in practice, if you see, that is not the case, because the infinities behave somewhat slightly different. So, when you take n cross n, it has exactly as many number of elements as n. So, that is what happens, and we will prove that rigorously in the later part of the course. But what I want to do, I want to just define a function. So, to define a function, then I need to say like what is the image of given element. Okay. So, let us say like maybe I will turn the tables. So, maybe I will define a function from n to n cross n. Okay. So, let us say, so I want to define a function from n to n cross n, and if you think about it, the function that I am going to define is actually a bijective function. So, which is that will actually give you injective function from n cross n to n. Anyway, I will leave it to you to think, but the upshot here is one can use any kind of rules in order to define a function. So, to define this function, what we will do, we will use this diagonalization technique. So, we are going to just list all the elements. So, we list the elements like this 1 1, okay. So, we have 0 also. So, 0 1 0 0, 0 1 and then 0 2 and 0 3 and so on, and similarly you have 1 0, 1 1, 1 2, 1 3 and so on, and then 2 0, 2 1 and then 2 2, 2 3 and so on. So, what I am trying to do here, I am trying to like list all the elements of n cross n as arrays. Okay. In the first row, I take all the elements that has the first component 0. So, 0 comma 0, 0 comma 1 and so on. Similarly, 1 comma 0, 1 comma 1, 1 comma 2, they lie in the second row and so on. So, now what I want to do, I want to define a function from n to n cross n. So, what I need to say, like for example, where 0 goes and then where 1 goes and where 2 goes. Okay. This is what I need to say. So, where is 0 is mapped, where is 1 is mapped and where is 2 is mapped. So, for that, so I am going to just use this following trick. So, if I actually kind of start kind of counting it from like horizontally, you can see that if I take 0 is mapped here and then 1 is mapped here and so on, then the problem is this never ends. So, then I do not know whether I will be able to kind of count all the numbers or the map all the elements in n cross n. So, that is why what we are going to do, we are going to do this simple trick. So, what we are going to do, we are going to say that this is mapped to 0. So, 0 is mapped to this, okay. And then we will go diagonally. So, we just go to the next diagonal. So, these are all the diagonals for us. So, then what we are going to do, so we use this path. So, we go from here and then move here and then come here and then go this bottom and then move here and then move all the way up and then come here and then move like this. So, from this trick you can see that all the numbers will be covered. Okay. So, that means what? That means, so what I am going to do, I will take 0 and then 0 map to 0 comma 0, and then I take 1 and then that I map it to 0 comma 1, and then I take 2 and then map that to 1 comma 0, and then I take 3 and then map it to this, and then I take 4 and then map it to this, and then I take 5 and then map it to this, and so on. Okay. So, then the procedure is clear. So, then I have told which natural number should be mapped to which one, and then it is very clear that the way I am mapping, and this indeed becomes injective map, and it is not only injective, it is also what is called onto map. So, we say a function from A to B is onto or surjective if f of A is exactly equal to B. The image of A is exactly B. What is the meaning of that? So, given each element in B, we will be able to find a pre-image in A. That is what ontoness means. Okay. And this map that I have described here, that actually tells whatever the function that I defined is indeed both injective as well as surjective, and such maps are called bijective maps. Okay. So, we say f from A to B is bijective. So, then the first condition is it is onto. The second condition is f is 1 to 1, that means f of A equal to f of B should imply that A equal to B for all A comma B in capital A. Okay. This is what called 1 to 1. Okay. So, this is mathematical definition of bijective. Bijective means both onto as well as 1 to 1, that means both surjective as well as injective. Usually the surjective and injective, those words are used in algebra a lot, and in basic analysis we use onto and 1 to 1. Anyway, it is interchangeable. So, it is clear like what is the meaning of bijective. So, the map that we defined, f is from n to n, which is takes n to 2n, you can easily see that this is indeed 1 to 1 map, but not onto, because if I take so 2n equal to 2m, then I can cancel out 2, then that will give you n equal to m. So, this proves 1 to 1, but 1 is there in n, but if I look at f of n, then this consisting of all even natural numbers, even numbers. Okay. So, that means 1 is not in f of n. So, that means f of n is smaller subset than n. So, that means it is not onto. Okay. So, we can have various possible functions. Okay. We can also have like constant function. Okay. Constant functions are, it takes only one value. Okay. F from A to B is called constant if, look at f of A, it is just some singleton B, okay, because all of them map to one element. So, that is what called constant. So, let us actually try to write down not bijective. Okay. So, here is the negation that we want to write down. So, f is not bijective. Okay. F is bijective, the negation will be f is not bijective. But what does it mean? That means it is either not onto or not 1 to 1. Okay. So, this is same as saying f is either not onto or not one to one. Okay. So, one of them will be violated. So, that means this is equivalent to saying f of a either f of a is not equal to b. So, that is the meaning of not onto, or there exists a tuple a b inside capital A such that f of a is equal to f of b. So, that is the meaning of, so this is the meaning of not one to one. Okay. Sorry. So, these two are same. So, this is something that like I said, you should actually get used to it, how to write negation for all the definitions that are you are encountering in mathematics, and that actually kind of helps you to write down proofs in more rigorous way. Okay. Otherwise, you struggle a lot in writing proofs. Okay. If you want to improve writing proofs, then better like you start actually writing down negations in more rigorous way. Okay, I will stop here, and we will discuss about various special functions in the next class. Thanks.